Well, hello, everybody. Welcome to the Stats for the Masses webinar, ChiSquare and Friends. My name is Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. Thank you for taking time to join us live. In fact, thank you to everybody for your interest in our webinars. I really enjoy putting these together. Today I'm going to present a very simple overview of analyses that we can use with discrete or categorical data. We're going to cover ChiSquare tests, Fischers exact tests, some other things. We're going to be using SPSS for our analyses today. Remember that today is just an overview, but I hope that information you receive today will give you some ideas and guidance on how to make use of categorical analysis in your research. As I say in all of our webinars, use what you learned today and apply it in a holistic way. Think about the big picture, not just the how, but the why of your study. When you get your results, you got to ask yourself, what does it all mean? And as always, it's my hope that if nothing else, you're going to come away from today's presentation feeling a little bit more in control of your capabilities as a researcher. My goal with the Stats for the Masses series and for Omega Statistics as a company is to inform and educate everyone about statistical concepts in a way that we all can understand. Sometimes that's not so easy, but we try to do our best so that everyone can see how elegant and useful statistics really are. We do have quite a bit to go over today, but I'm hoping to cover the presentation in about 45 minutes or so, so we have some time at the end for some questions and answers. Okay, now I've currently muted the line so only my voice can be heard, but our assistant statistician Brianna Ramirez is monitoring the chat board, so feel free to type any questions you have on the chat board and Brianna will choose some to ask me at the end of the presentation, and she'll also try to assist you with any technical problems you might experience. If you do have technical issues, I often find that just logging out and back into the webinar clears up just about everything, so I say when in doubt, reboot. And so let me go ahead and we'll get started. Before we actually begin, I want to take a minute to tell you about Omega Statistics. And after the webinar, I'll also take some time to tell you about some of the happenings here at Omega Statistics and with the Stats for the Masses webinars, newsletters, some latest news. But for Omega Statistics, we are a private practice statistical consultancy. We're based in Southern California. We do medical and clinical research. We handle clinical trials phases 1 through 4. We do perform design and analysis of experiments. We work with epidemiology studies, large data, journal article assistance for researchers. We do provide dissertation assistance for your methods and results chapters. I think we're the best in the country, and so do our clients. We do help with survey design. We also help with projects of any size. You could be an individual researcher, small business, a startup, large corporations. We help government too. We actually, anything statistical, we're there. Our motto is to provide elegant solutions effectively applied. We also have a new division now. We just launched it this month. It's called Clone, and Clone is going to help Omega Statistics in a way. It provides editing, transcription, data processing services, and here's our web address for the new division. Okay, so big question, what is ChiSquare? What is ChiSquare? Well, it's many things. ChiSquare is a term that we see in many different contexts. It's a distribution, and here's the distribution. Here it is with different degrees of freedom. As you can see, kind of it has a long skew to the right. It's not quite a normal bell shape like a normal distribution. It actually looks like half of a normal distribution. Usually starts at 0. It can go all the way up to infinity. And the reason is because it uses discrete count variables. And so you start at 0 and go up. So it is different from a normal distribution in that sense. Normal distributions go from negative infinity to infinity. This one just goes from 0 to infinity. Let's see, it's also a term we see in many different contexts, such as a statistic. Here's a simple one whenever we're doing the goodness of fit, which will be the first test that we cover today. And it's just you sum up all your observed minus your expected, you square it, divide it by the expected. We'll see that a little bit. I'm not really going to get too much into the mathematics of it today. It's basically just what context the chi-squares would be used in, and also how to maybe run them in SPSS. Chi-square is also a part of many analyses used to test discrete variables. We have the goodness of fit test we'll cover today. We're also going to cover the test of independence. It's used in the chi-square statistic is used in logistic regression. It's used in many, many other types of analyses also. You see it quite a bit. Why use it? Well, often we want to investigate the association between discrete variables, and that is numerical variables that are not continuous. That also might sound like another language. However, what that means is that it uses chi-square uses the variables that are numbers. They're represented by counts or represented by categories. How many are in this group? How many are in that group? Not variables with decimal places. If you see a decimal place, most likely that's a continuous variable. Okay, if it's a count like 1, 2, 3, 4, then it would be a discrete. Chi-square is not used on means. It's not used on proportions, even though you are looking at proportions when you use it. It's not used on outcomes that are percentages, although you do look at percentages when you use it. It's only used on the counting type of number. So the range is 0 to infinity, as I said before, no negative numbers. Examples of discrete variables, they can't be made into smaller pieces. So today we're going to be looking at the numbers of M&Ms in a bag. Number of females in the stats lab, how many times I had to let the dogs out last night. Okay, examples of continuous variables, which can be made into smaller pieces, are my weight gain from eating M&Ms, my GPA from the stats lab, and the number of seconds it took for the dogs to scratch on the door to come back in after I let them out, which is anywhere with a range from 0 to 3 seconds, it seems like. We need to know a little bit more of the terminology. Chi-square makes use of something called contingency tables. A contingency table is a chart of frequency counts, the numbers, of the categories for our variables, and you're going to see many of those today. They're also called cross-tabulation table, crosstabs, frequency charts. We'll see a couple of crosstabs in this webinar. Observed counts. Those are the number of items that we actually count or observe when we're doing our study and we're looking at how many M&Ms are in a bag. That is an observed count. Okay, an expected count, that's the number of items that we would expect to see. We aren't counting them. We would just be from the formulas that we derive. Actually, the chi-square test brings back the expected values in a lot of the instances in the software. We'll learn more about this as we go through it. Expected counts are often set prior to analysis, but the observed counts are measured by the researcher, which would be you or me. Assumptions. There's two assumptions for a chi-square analysis. Well, there's the main overall assumption for most analyses, which is that you should be pulling them from a random sample. However, most of our studies don't include random samples, so that is often a relaxed assumption. An individual count can only be represented in one cell of the contingency table. That means that each person can only be represented in one cell. They shouldn't be, if you have a yes and no category, you can't be both yes and no. You can only be one or the other. No more than 20% of the cells in the contingency table can have an expected count of less than 5. People get confused on that. They will look at the chi-square table and they'll see that they have a value in the cell, one of the cells of less than 5. That's okay to have a value of less than 5, an observed count less than 5. However, you shouldn't have an expected count less than 5. None of the cells in the contingency table should have an expected count of less than 1 either. You can have an expected count of 0.5, as long as no more than 20% have something like that. And we'll see as we go through. Some of the tests we're going to cover today are the goodness of fit, chi-square test of independence, Fisher exact test, McNamara's test. If we have time, we're going to look at something called Simpsons Paradox, and I'm also going to share some gossip on two of our founding fathers of stats, Karl Pearson and R.A. Fischer. Pearson is famous for these chi-square tests, and Fischer, of course, the Fischer exact test. Okay, so let's go ahead and get started. And start with the goodness of fit test. That's probably the simplest. It's used to compare an observed distribution, which would be something that we've seen or something that we've measured, to a hypothesized distribution, what we would expect, what we would plan to see, what we would like to see. The example, you may have seen this example before. In fact, I saw it as an undergrad, which I thought was very, very cool, and it allowed me actually to go buy some M&Ms yesterday, which I love to do. Mars companies spent some time and money on consumer preference tests to develop a color distribution of the M&Ms in each bag. And their color distribution is supposed to be one that pleased the greatest number of people and created the most attractive overall effect. According to Mars, the color proportions of a plain bag of M&Ms are as follows. They want 24% of them to be blue, 20% to be orange, 16% to be green, 14% yellow, and 13 each red and brown. If you add those up, you will notice that they come to 100%. So it should include all the M&Ms in a bag, and this is what you would expect. Now, these aren't counts, these are percentages. However, I'll show you how to make them into counts. So I bought a bag of plain M&Ms from the vending machine down the hall, and I wanted to see if the colors in the bag matched the expected distribution. So I hypothesized the following. My null hypothesis was that the color distribution in the bag is consistent with the distribution desired by Mars. The alternative was that it was different, right? Your null hypothesis is always the one where there's nothing going on, nothing different, everything's equal, right? Your alternative usually is the one that you're actually interested in. You're thinking, wow, is my bag different, right? So my bag had 55 M&Ms. Actually had 56, but as I was walking back to the office, I ate one and I didn't see what color it was. I forgot that I was going to use them. So we'll say I had 55. So from knowing that I have 55 M&Ms, I can figure my expected counts, right? Here's my percentages here that we just went over on the previous slide. So I just take 55 and I multiply it by 0.24 to get this. This would be my expected count. Okay, and it's the same thing similarly for all of them. Okay, as you can see, these numbers have decimal places, so what we'll probably do is round them up, right? So we'll say this is 13, we'll say this should be 9, this should be 8. Whenever you do get the output from SPS or your software program, your expected counts do come back oftentimes with decimal places. It's just the nature of it. However, we do know that, you know, a discrete variable, at least what we're observing, we won't be looking at 13.2 M&Ms. We'll just be looking for 13. All right, so let's start building a contingency table. So since we got to have discrete variables, so we're going to need to round up or down, like I was saying before. So here's how I rounded them for the expected counts. So I took this 13.2 and just made it 13. So on and so on, okay? And then I'm going to check it. So I add up all of them, make sure that they come out to 55, okay? So that way I know that everything's been covered. So I plugged them into the table. Now we need to compute our observed value. So that's the easiest part. I just count the M&Ms for each color. So here's what were in the bag. I had 16 blue, I had 8 orange, 18 green, 2 yellow, 4 red, and 7 brown. Well, I can see right here when I put them into the table, I'll also add them up, make sure they add up to 55, okay? So when I plug them in, I can see, you know, this is a little higher than expected, that's a little lower than expected, that's twice as much as expected. When I run the ChiSquare, I'll be interested to see that. I think that's a big deviation there from the expected distribution. That's much lower, okay? Brown's right on. Right? So this looks different to me, right? But is it statistically significantly different? Let's see. Let's see. Oh, I'm going to set it for a 95% level of significance, which means that we're going to reject the null hypothesis if our probability value or our p-value is less than 0.05, which is the standard. And we could use that formula But we have a lot to cover today, so I'm not going to do that. We're going to use some software instead. So let's go in and do that. So I'm going to go in and get my data here for the goodness of fit. I already put them in here, so let's warm up SPSS here. Okay. All right, so here are the different colors. So what I did was I put them in, I kind of had, for some reason, SPSS wanted me to make them numeric, even though they're not numeric. They are actually values of colors. So what I did was I assigned them. 1 was blue, 2 was orange, 3 was green, and so on. Okay. And then we have the counts over here. So these were my observed counts, the ones that were actually in the bag. So here's my green. I coded it as 3 with the 18. And what we're going to do is we're going to run this chi-square goodness of fit, and we're going to see what we get. So let's go into analyze. And then, oh, you know what? First, let's do it this way. There are ways that you can do this. Maybe oftentimes you would see something with very, very long, drawn out thing where you would say color 1, color 1, color 1, color 1. You'd have this really long line down here of 55 records, right? This is an easier way of doing it. You can just plug in your numbers and you can do this thing with weighting. So I'll go into data. I'm going to weight to cases. I'm going to weight by count. Okay, let me take that out of there. Then I'm going to go into analyze. And then I'm going to go down into non-parametric tests. And then I'm going to go, let's see, I will go here into legacy dialogues. I like the legacy dialogues better. I'm going to go into the chi-square. Okay, now I'm going to say, okay, color is going to be our test variable. So I'll put it over here. Now you have the option down here where you could say, I want all the categories to be equal, right? And with 6 categories, what would that be? 100 divided by 6. That would mean that we would want about 16.67% in each group. However, that's not how M&Ms wanted it. They said that they had certain criteria they wanted. So we're going to give it values. So we know that I already have it ordered from blue, orange, green, yellow, red, and brown. So I'm going to add in these proportions in the same order. So blue was 24%, so I'm going to add that. Okay, and an orange was 20%, so I'm going to click add to add that. And then let's see, green was what, 16? So I'm going to add that. And then I'm going to add 14% for yellow. And then we have 13 each for the other 2. And let me do that. Let's try again. Add, and then 0.13, add. Let me make sure they're there. 24, 20, 16, 14, 13, 13. Looks like that one. See that? I didn't put a decimal point. 0.13, right? Okay, now they all have their little decimal points. All the numbers are correct. And I'm going to click OK. And there we have our output. All right, so let's see what this means. So to the left is the output that we just saw. Okay, we can see the observed counts, what was in the bag. And here's our expected counts with the decimal places, just like we figured before we rounded them. And also the p-value is down here. 0.005, it's less than 0.05. So it's actually significant. And don't forget to check your assumptions. So SPSS is kind enough to let us know how many cells have those expected frequencies of less than 5. As you can see, none of them do. So we're fine. Now we can conclude that the counts of M&Ms in the bag were not consistent with the expected counts. So therefore, we're going to reject the null hypothesis that the color distribution in the bag is consistent. Okay, so my bag was different. And that's how you do the chi-square goodness of fit. Now, if you look at these residuals here, we'll go over these in a little bit, and I'll show you what they mean. But they're very, very helpful. They take your analyses one step further, and I'll show you those in a little bit. Let's do the chi-square test of independence now. Okay, so the chi-square test of independence, it compares two variables. So you're not taking your observed information and comparing it to some hypothesized distribution. You're actually comparing two different variables to see if there's some differences going on between them, or if they're independent of each other, which means nothing's going on between them, or if something might be having some kind of effect. So it's used to test if the proportions of counts on one variable are the same as the proportions on the second. So each of the two variables needs at least two categories or levels, and that's called a 2x2 table. So you're often going to see tests for a 2x2 contingency table. And the 2x2 means 2 rows by 2 columns. Rows are always first, columns are always second. Okay. So when you see this notation, you'll know that. And also, sometimes you'll see people talk about hypothetically an R by C table. Chi-square doesn't have to be 2x2. It could be, 20 by 40 if you have a big enough sample. I mean, it could be any size you want, really. Tables can be as large as you want, as long as your assumptions are met. But when you see R by C, R means row, C means column. And you're also going to see degrees of freedom quite a bit for the chi-square test. Degrees of freedom are computed as the rows, number of rows minus 1, times the number of columns minus 1. So therefore, if you had a 2x2 table, you're going to have 1 degree of freedom because you have 2 rows minus 1, 2 columns minus 1, so you have 1 times 1, which is 1. Okay, so you'll see those quite a bit. The people I were telling you about a little bit earlier, Pearson and Fischer, had a big argument about degrees of freedom. One of many disagreements between them. And I won't go into it today, but if you want to read about them, I'm sure you can find the information on that. So I'm going to give an example. I think for the rest of this webinar, it's going to be the same kind of example. My husband's name is Rod, and Rod and I love to play board games, and he is awesome at backgammon. He's an ace. I, on the other hand, I'm not so good at it, but I do seem to be able to read his mind on Battleship, and for some reason I know exactly where he's put those boats, and I destroy his fleet in no time. So let's look at some data and test some hypotheses. Now, these are all for fun. No official studies were done. I just kind of needed some numbers, and I needed something fun to work with. But it applies. The null hypothesis would be that the proportion of games won by Rod and Elaine are the same, whether we play backgammon or Battleship. The alternative is that there's differences. Maybe one of us is better than the other. There's something going. It's contingent on the game. There's something going on, right? This is a two-sided hypothesis. Now, I could have also used a one-sided, where I could have said Rod is way better at backgammon than Battleship. Is he? Right? Is he way better? And then that would have been one-sided because we're not looking to see, if Rod and Elaine differ on the two different games. We're looking to see if one person's better. The steps are the same, except I would divide the p-value by 2 if I'm doing it one-sided. However, we're just going to look at the 2x2 two-sided test today. We could also look at more games. We could look at more people. Right? So we could have 20 players and 20 games and see, if there's any differences there, if you get a big enough sample. Let's go ahead and run the numbers. Let me go in here. Let me go ahead and open up for independence. Here's how I put it in. Again, you could have it where you would put game, winner, all the way down for 15, where I'd have backgammon Rod 15 times, and backgammon Elaine 5 times, right? And I could just go down and have a very long bunch of data. And that would be very time consuming, and boy, you could make mistakes a lot easier. This way is simpler. So let's go ahead and do the weighting with the count again. So I'm going to go in data. I'll weight them. I'm going to weight it with the count. And then I'm going to go in and I'm going to analyze. I'm going to go this time into crosstabs. I'm going to go descriptive statistics. I'm going to go down to crosstabs. For my row, I'm going to make it the game. Okay. And for the columns, I'm going to put the player, who was the winner. Okay. And then I'll go into here where I have statistics. I'm going to pick chi-square. I'm going to hit continue. For cells, I like to look at the observed, I like to look at the expected, I also like to look at percentages just to see what the different percentages are. And then I also like to look at the adjusted standardized residuals, and these are the residuals I kind of mentioned a little bit earlier. I'm going to hit continue, and I'm going to click OK. And here we have our output. It shows there was 60 observations. Here's how they are all divided. Okay, and here's our significance. Let's go back into the PowerPoint. All right, so here's the same contingency table that we just saw. Has quite a bit of information, but right down here is your ChiSquare statistic. See, it's rather large. When you see big test statistics, then you can most likely assume that you're going to have significance, which we do. It's less than 0.05. Okay, means something's going on there. So we know that the player's success at board games is not similar between backgammon and Battleship, right? One of us might be better than the other at one or the other. So this is nice to know, okay? And that's what this tells me. But I want to know more. I want to know not just if a player's success depends on the game that's being played, but I also want to know which player and which game, who's better at which game. And I can get more of an idea of this by looking at the adjusted residuals instead of just saying, okay, yeah, there's a difference, it's significant, there's something going on there, something's dependent on the game. It'll tell me kind of an idea of what, right? Because you'd want to know why. So what we're doing is we're taking these adjusted residuals and we're going to look for a cell with an absolute value. So it could be negative or positive, but it's got to be bigger than a 2 or a 3. Okay, and if you see those, then that indicates that that cell contributed more to that significance. The residual indicates a greater contribution to the overall effect of the significance. Okay, so let's go ahead and look at this again. This means that Rod wins at backgammon much more than expected. So here we go. Here's Rod. Here's the winner, right? Rod and backgammon. He won 15 games out of 20. Here's 20 games. He won 15. We only expected 8.3. All things being equal, we would only expect at he'd win about 8 games. But he won 15. Our residual down here is 3.7. Okay. When they're positive, that means they're more than expected. Okay, and here it is. He won more games than expected. If it is a negative number, that means fewer games than expected. If we look down here, here's Rod again. Here's Battleship. So we go across. He won 10 Battleship games out of 40. There's our total. So out of 40 games, he won 10. We only expected, but we did expect that all things being equal, he would have won almost 17. So he actually won less than expected. So there's your negative residual. Okay. Now note the total column. We don't need to have the exact same number of games for each game type. Okay. We played 20 games of backgammon. We played 40 games of Battleship. And I said this is usually because I stopped playing the game after losing 1 or 2 games. Rod will keep going until he wins. He wins if it takes all evening. Okay. However, I can't say that's statistically significant. Anecdotally, I'm a poor sport. I start losing. I don't want to play. So that's why we probably only played 20 games versus 40 of Battleship. I said that's enough. So that would be for the chi-square test of independence. Now, sometimes you don't meet the assumptions, okay, for the chi-square. And we have to remember what they were. An individual count can only be represented in one cell of the contingency table. And no more than 20% of the cells can have an expected count of less than 5. Okay, and none of them can have an expected count of less than 1. Well, there might be times when you don't have enough data to meet those assumptions. Then you can use Fischers' exact test. The only assumption you need is that you're only represented in one cell. Okay, that your individual count can only be in one cell. And you can even have 0 counts in some of the cells, and that's okay. So although Fischers' exact test can be performed on R by C tables, so they can be as big as you need them to be, SPSS can handle Fischers' exact test only for a 2x2 contingency table unless you purchase the exact test package from them. I don't have the exact test package. Whenever I have a table that's bigger than a 2x2, I usually use R software and write code and use it that way. In fact, maybe I can see if I can figure out how the blog space works and post some code for you. The process in SPSS for computing the Fischers exact test on a 2x2 table is the same as for the chi-square. And in fact, they shoot out the p-value for the Fischers in the output. So we can try it really quick. Here's an example. Rod and I are having game night. So we start with backgammon, and Rod wins all 3 games. Then I decide if we're going to play any more, then we should play Battleship, because I'm not going to lose anymore. So I win 5 games, and then I lose 1 and decide I'm done. Okay, and then I said, oh, come on, we played 9 games. So 9 games on any game night is enough. But here's our contingency table. So here's the number of wins for Rod at backgammon and Battleship. And I didn't win any at backgammon, 5 at Battleship. And in total, Rod won 4 games in total, I won 5 in total. Here's all our totals. Okay, and basically you can just read them across down, and you can get, these are called marginal totals because they're on the margins. That's why. All right, so we violated the count assumption for the chi-square. Okay, you can see right here, there's 0, right? Here's our expected counts. Look at them. They're all under 5, right? Let's go ahead and run it, though. I should do that. It's just the same way. So I'm going to open up this data, backgammon here, and then here's where the winner. So here's where Rod won backgammon 3 times. Elaine won backgammon 0 times. Rod won Battleship 1 time, and I won 5 times. Okay, so we're going to weight again. Data, we're going to weight it. Going to weight it by count. Okay, so we're going to go into analyze. We're going to go right back in here. Okay, I'm going to put in game as the row and winner as the column. And there's statistics there. We'll ask for the chi-square, why not? And everything else we're going to have the same. Let's make sure. Oop. Go ahead and put these in. And that. Okay. So here's our output. There's the 9 games. Here's the 9 games down here too. Your marginals always add up here to your grand total. Okay. Let's look down here. There's your chi-square statistic, but we can't really use that because it doesn't meet the assumptions, right? So right down here is a Fischers exact test, and it's significant, 0.048, very close to 0.05, but it's still significant, okay? And right here it tells me that all my cells, 4 cells, 1, 2, 3, 4, all 4 of these have an expected count of less than 5, and they do. And there you go. So we violated it, but we can go ahead and use this number. So we still have the residuals down here too, and they're bigger than a 2, right? And again, it looks like Rod has a positive residual here. So at backgammon, he did better than expected, right? We observed 3, but we expected 1.3. I did better at Battleship. I won 5, but we expected I'd only win about 3.3. Okay, and again, look at the symmetry. In a 2x2 table, you always see this kind of symmetry. Here's this, there's this, there's this, there's this, right? One's positive, one's negative. One's positive is negative. Kind of interesting. It doesn't look like that whenever you have larger tables, but I just think it's really neat for the 2x2. So we can come to some conclusions. Rod's still not very good at Battleship. Nope, he's not. Or Rod's pretty darn good at backgammon. Yeah. And I'm a stellar Battleship player. We could also conclude that I don't care much for backgammon anyway, because I'm a poor sport. So there's Fischers exact test. Very useful. Okay, I promised that we might look at something with a repeated measures element, okay, and it's called McNamar's test. It's also an exact test, and it's a chi-square for repeated measures. There's some analyses for handling this besides McNamar's, but we're going to look at McNamar's today. For a McNamar's test, you want your dependent variable to be binary, yes, no, either or, one or the other. It's like a paired t-test. And it's used when the same individuals are measured twice or the subjects are matched in some way. Maybe you have twins, couples, I said eyes, feet. A lot of times that's true. You will do a study maybe on eye drops, and you want to have maybe one drop in a left eye and a different drop in the right eye. Or you want to have the same type of drops and just see if it works differently on the left or right. Usually not. Usually you have one type of a prescription in one and one prescription in another, or one treatment in one and one treatment in another. Same thing with feet, hands, things like that. Anytime you have a pair. By now, we all know that Rod is an ace backgammon player, and he's a great sport. But does playing backgammon with Rod have an effect on a person favoring backgammon over Battleship? Does it change their game preference? So our study now, we took 380 people who stated whether they favored backgammon over Battleship. We just asked them, okay, 380 people, which do you like better? Okay, and they told us, so we took note of it. And then each person played 5 games of backgammon with Rod. Boy, was he busy. He's tired. But after they recovered sufficiently from their defeat, they were asked again if they preferred backgammon over Battleship. The study's totally hypothetical, probably fundamentally flawed because the participants didn't get to play Battleship, right? They just got to play one game, and they only got to play with one person. But we're going to go with this for demonstration purposes. Okay, so there's the information again. Here's our contingency table. Now notice it looks a little bit different because on this side, the rows are going to be before and the columns are going to be after. That's our repeated measures, okay? So before, we had people that before to after. It's a little bit more complicated. 100 people liked Battleship before and also preferred Battleship after, okay? Then 120 people preferred Battleship before, but then afterwards they liked backgammon, okay? And here, down here, 30 people liked backgammon before, but afterwards liked Battleship, okay? And then these last 130 here, they liked backgammon. They didn't change their mind. They liked it before and they liked it after. So basically that's what you do. You just go across and you go down, you look at the number, and you can kind of see what it means. Altogether, the number of people who liked Battleship here before, 220. And the number of people who liked backgammon before, 160. And then here after, 130 and 250, okay? But it's the same subject. Some of them just changed their mind. Some of them stayed consistent. Let's go ahead and run that. Go back in. Here's my data for McNamara. This is a little bit different. So here I have before and after, and then I have the count, and it kind of matches that contingency table. So the people that liked backgammon before, but Battleship after, there were 30 of them. The people who liked backgammon, but then still liked backgammon after, 130. So you kind of get it. Battleship to Battleship, they didn't change their mind on Battleship, 100 people. Okay, so now we're going to run it. And, oh, we're going to weight it first. Let's go into this. Weight cases, count. Okay, then we're going to go into analyze, and we're going to go in here. Piece of cake, it's just basically, I'll make rows before, columns after. It's basically you just have to click one more thing. McNamara. I'm going to ask for the chi-square too. Why not? Not that it's going to be legitimate for this analysis, but just to show. And in a way, it's kind of nice to show this because if you click a cell or click a option, you'll probably get numbers where it doesn't mean that it's right. Right? That you'll just get numbers. So that's why it's important to set up your study well and know kind of what you're doing. SPSS will give you values. So here's our cells. And I'm going to click the same kind of things. I'm going to look if I can get residuals again. Okay. All right. So now here's our nice big cross tabulation again. There's our 380 people, and they're down here. Okay. Here's our counts, our observed counts, our expected counts. Look at, we got our residuals again, right? And then down here's our significance. So like I said, you will get a value for chi-square. Doesn't mean it's worth anything. I got a value for Fischers exact test here too because it is a 2 by 2 table. But what we really want here is the McNamara's test, which is this, exact, okay? And it's less than 0.05, so therefore it's significant. Okay, so as I was saying, the results are significant. Here's our table so you can kind of match them up. It kind of does it backwards for this one because the SPSS does alphabetical. So it'll put backgammon before battleship, even though I put battleship before backgammon here. But you can kind of see, here's the 130, backgammon, backgammon. So I just go here, backgammon, backgammon. There's the 130. So it's kind of turned. So you need to be careful of that. But just kind of pay attention to what you have here, and it'll kind of tell you. There's a lot of information in here, but what I'm really interested in here are these totals. I'm interested in the total going across for backgammon, and I'm interested in the total going down here. Well, the total before and total after for the backgammon. I want to see how it's looking for backgammon. Okay. Before the backgammon intervention, 42.1% of the people preferred backgammon, because here's our before and here's percent in the total. 42.1% liked backgammon altogether. Okay. After the intervention, I go down here, down the column, 65.8% preferred backgammon. So playing with Rod actually increased the player's favorability towards backgammon over battleship. Okay, so my conclusion would be that playing backgammon with Rod makes the game better. And he is good company, and it is a very biased conclusion. And it's all made up. However, for demonstration purposes, it's good. But yeah, so you can have a repeated measures. There's also other tests, Cochrane Mantel-Hansel test, lots of big names, and too many to go over today, but I'll have some references here at the end that I can show you. Let's look at Simpsons Paradox. We have a little bit of time. Good. Let me get a sip of water. Okay. Simpsons Paradox happens whenever you have a trend that appears in different subgroups. But it disappears or it changes direction. It'll go the exact opposite way when you put everything together. Okay, so I've had it happen a couple times. I've had it where I had a study with doctors and nurses, and they had different directions. But then whenever we put them together, all of a sudden everything changed. It's just totally changed directions. And it's often to do sometimes because you're looking at two different populations, subpopulations, when you shouldn't. And but let's go ahead and look at an example really quick. We have two groups of people, video gamers and Mensons. And we assigned them into two treatments of playing either backgammon or battleship. And we asked them if they were having fun. So let's look at a summary table. I'm not going to show a great big table or anything like that. We're just going to look at the summary table just to give you an idea of what a Simpsons paradox is. The video gamers, let's see, all together we had 80 and 40, so we had 120, right? Out of the 40 that were assigned to playing backgammon, 10 of them liked it. They were enjoying themselves, okay? Out of the 80 that were assigned to battleship, 22 were enjoying themselves, okay? And it's the same thing down here. Of the 80 Mensons who were assigned to backgammon, 60 of them were having a great time. And of the 40 of the Mensons that were assigned to play battleship, 35, they were having a good time too. So you can look at the percentages here. Of the video gamers, it looks like they prefer battleship a little bit more, 27.5% over 25% were enjoying themselves, okay? And with the Mensons, 87% really liked battleship, it seems, compared to backgammon, a lot more were enjoying themselves, okay? So right here, you're looking at this going, okay, for video gamers and for the Mensons, they like battleship better, okay? But whenever you combine them all together, look what happens. You have 120 here, because 40 plus 80 is 120. 70 people were enjoying themselves playing backgammon, okay? And here we have 120 people. 57 people were enjoying playing battleship, less, 58%. So what happened? You know, here everybody likes battleship, but when we put them all together, oh, what happened? Now they like backgammon. So why is that? Well, there could be a couple reasons. The sampling was unbalanced. That's the big one. They weren't assigned equally, right? Here, for the video gamers, we assigned 40 to backgammon and 80 to play Battleship. But for the Mensons, we assigned 80 to play backgammon and 40 to play Battleship. We did opposite, right? We could have done 50-50. It probably would have been better, which would have been 60 a group. Okay. The other one is that perhaps gamers and Mensons are different populations of people. So when combined, it's possible that these differences are going to be washed out. So when you're looking at subgroups of a population, your population should have some kind of maybe homogeneity to begin with, some similarities to begin with. Don't make your subpopulations two different things and then try to combine them as if they're all kind of similar. And that's basically what that is. So the conclusion on this, be careful with how you design your study. Okay. So what do we have left? Oh, this might be something. I'll just go over it really quick. Karl Pearson is the man who basically invented the chi-square. Pearson, you'll hear Pearson's chi-square. Pearson did correlation. He did a lot of things, okay? R.A. Fischer, well, that's Fischer's exact test. He was the one that thought of maximum likelihood estimation way back at the turn of the century. And they were around the turn of the century. Karl Pearson was already famous, already popular, already well known in statistical circles at the time R.A. Fischer was coming up. And R.A. Fischer is brilliant. Came up with some ideas, especially the maximum likelihood. Well, Pearson didn't agree, shot it down, and also, not only did he do that, he wrote a paper rebutting R.A. Fischer's ideas and basically cut them down in the paper. R.A. Fischer said he wouldn't have minded that if Pearson would have told him. Okay, Pearson didn't tell him. He just went ahead and published it and said, well, I don't agree with R.A. Fischer. I don't think he's right. He's wrong. Well, that caused think about it. You have a very respected person shooting you down, and you're trying to get your foot in the door, and you're coming up with these great ideas, but nobody wants to listen to you. R.A. Fischer actually couldn't get some jobs because of it. He couldn't get some things published because of it. So he basically did not like Pearson. In fact, he didn't like Pearson so much that, for years and years and years, after Pearson was long gone and long dead, he still would say things about Pearson that he could not, did not like him. Pearson had a son, Egon, and who was Pearson very, very protected him very much, kind of kept him sheltered. So Egon was kind of a quiet type. And so he didn't really, want to cause waves or anything. Well, it turned out that Egon and R.A. Fischer, actually, I think it was Cambridge that they ended up working at. They were both chairs of departments in Cambridge in the same building. However, R.A. Fischer was so angry at Karl Pearson still and couldn't stand Pearson that much and his own son. They had to walk up separate staircases. A lot of buildings will have a staircase on one side of the building and another one on the other side. They purposely would only walk on their designated staircases so they would never have to see each other. Okay, so there's some drama out there in science, and there's some things going on out there in science. In fact, another thing that's kind of funny about it is Pearson's son actually studied R.A. Fischer's ideas in journal articles and actually came to the conclusion that R.A. Fischer was right and that his dad was wrong, which made it even harder. I could only imagine. But anyway, there's some gossip, there's some dish for the day. Let's go on and see what else we have here. Oh, here's some references. Okay, so you can teach yourself statistics. Just start with the chi-square. Actually, StatTrek is great. And check out that site. You can learn a lot about a lot of things. It's in nice plain English, makes it really simple. Handbook of Biological Sciences is another great online resource. And here's something about the chi-square. McNamara's test in more detail. Also a good company. And something we didn't cover today, but I think I mentioned it, was the CMH test. This test is used when you're looking at the same variables, but at different times or with different subjects. So it's not really a repeated measures per se. It's because the people are different. right? You're not looking at the same people like we did where we had the same 380 people before and after. You might be looking at the same variables, but maybe you're looking at spring and fall or something like that. Here's something, I think it has to do with leg warmers and people's preference. And it's also, oh, it's the same company. Oh, wait a minute. You know what? I put the wrong link in there. It's not the same company. I'll find that and I'll change it on this PDF on the document for you. But that's it for that. Okay, we've got a couple minutes. You can probably read about this later. You can go, we do have some more webinars coming up. Next month is the literature review, how to do a literature review like a boss. So that'll be next month. And in August is going to be a power analysis again. People love that power analysis webinar. They keep asking for me to do it again, so I'm going to do it again in August. And let's go on and see what else we have here. Here's the thank you. And thank you. Thank you very much for attending. And let me see if I can bring Brianna in, and maybe she can ask us a couple questions. We do have about 5 minutes. So let me see how I get her on board. It's been a while since I've done this. So just a second here. Okay, I think I've unmuted you, Brianna. Can you hear me?
Yes, I'm here. Hello.
Okay, good. Do you have any questions for us?
I just have a couple this time.
Okay.
Okay, so my first question is, what exactly is an exact test?
I like that. What exactly is an exact test? Usually when you have a lot of our tests, the t-test and ANOVA, the ChiSquare, all go with a distribution, right? They're all based, you're making a guess and you're doing your computations according to how your data would react if it was meeting a certain distribution. So for a ChiSquare test, you're putting some elements into your computations to say, well, if my data was following a chi-square distribution, how rare would this result be? How would my numbers turn out? An exact test, on the other hand, doesn't use any distribution. It's basically just taking straight probabilities or straight numbers right from your data, okay? And that's the difference. If you look back, if we go back to some of the slides here, let me see if I can go back at all. Some of the output. Let's see. Here we go. See, the chi-square has a test statistic because we're using this to test against the distribution. It used to be a long time ago. You'd go back into a table, you'd get this number, and then you go into this big chi-square table, probably that Pearson put together, right? And you'd say, okay, is this significant? You know, is it bigger than a critical value from a table? If your number's bigger than a critical value, then you'd say, okay, I have significance. But if you look down here, the Fischers exact test, it doesn't have a value there. It has no test statistic because this is your exact probability just by doing the computations. So that's the difference. You just don't, okay. It's an exact test. There's no distributional qualities to worry about.
Okay, and then where can I find out how to perform Fisher's exact test for larger contingency tables?
Yeah, it's hard. It used to be that you really didn't want to do more than a 2x2 table for Fischers because they get really unwieldy. Of course, now with software, it's you can let the software to do work. I was going to say I don't know why SPSS doesn't do more than a 2x2, but they do. They just sell it to you in another module that you get to pay for. One of my pet peeves with SPSS is that they do kind of nickel and dime you for every little addition. But I won't go on and on about it because it is still a good software. I just don't like that aspect of it. R has a routine you can use to do more than a 2x2 table. In fact, we'll make a note of this, and whenever I send out the PDFs and the information and the recordings for the webinar, maybe I can also do a little handout that kind of shows you the code so that you can do more than a 2x2 on a Fischers with R software. And I think other softwares will do it, SAS and such, but I know for sure, whenever I need it for more than a 2x2, I go into R. So any more questions?
No, that was it. That was all the questions we had.
Okay. Okay, well, thank you again. Thank you, Brianna, for watching the board and
Oh,
answering
thank
any
you.
questions people might have had. And thank everybody for attending. And we're done just on time. And of course, if you have any questions, email me. Here's my email address. And take a look at our site and see what we have coming up. And of course, I guess that's it. Have a great summer. Have a great 4th of July. And hopefully, I'll see most of you guys at the end of next month.